Recall, I wrote, the magnetic field on a charge, and we did say the charge had to be moving perpendicularly to a magnetic field. We said magnetic force, and I used B because B is magnetic field, the symbol for magnetic field, was equal to QVB. I gave you all the notes, right? I gave them to you? Yeah, okay. Where these two had to be at right angles to each other. So now let's consider a specific example. Let's consider an electron. Which way is this electron traveling? To the? Now, we don't deal with electrons traveling to the right. An electron traveling to the right is the same as a proton traveling which way? To the? So let's all use my screen. We're going to point our thumbs to the left. Right thumbs pointing to the left. And it's hitting an external magnetic field, which is represented by those circles with X's. What direction is that external magnetic field meant to be? Jacob is correct. It's into the page. So you're going to extend your fingers into the page, like you're high-fiving. When the electron gets right there, what direction will it experience a force? So when the electron gets right here, it's going to get deflected down. And so now it's traveling right and down, which is the same as a proton traveling up and left. Point your thumbs this way. Which way is the magnetic field still into the page? Which way will this electron experience a force now? Down and left? Yes? And so now it's going to get bent down and left. So now it's traveling straight down, which is the same as a proton traveling straight. So you're going to point your right thumbs up, fingers into the page. Which way? Do you see what's happening? Darian, this electron is going to get bent into a half circle, but a circle. You know what that means? It means that we can say magnetic force is pushing us in a circle. The same way as when we were in orbit, we could say gravity is what was pulling us in a circle. It means, Dro, that we can say QVB equals m, because force is mass times acceleration. Don't write this next bit down, MAC. Don't write the AC, because there was two versions of AC. There was the 4 pi squared r over t squared and the v squared over r. Which one do I want? Hey, is there a v on the left-hand side? Then I'm thinking I want a v on the right-hand side. This is what you can write down. Magnetic force is what's pushing us in a circle. Oh, but Olivia, look. Dong! I can cross out one of them because there's a v on the left and there's a v squared on the right and they're both on the top. In fact, what I really get is this. QB equals mv over r. Now, none of this is on your formula sheet, but QVB is, and if you're moving in a circle along, well then, you're moving in mv squared over r. How many variables are there in this little expression right here? You know what? If I give you any 4, you can find the 5th. And now we're starting to talk about particle research. So for example, if you bent a particle and you measured its radius by either using machinery, or in the old days, they literally used film from a film canister, a big film plate, and you would see a smear and you would measure the radius with a ruler. You could then make a guess as to the mass of this mystery particle, or the charge of this mystery particle, or how fast it was going. Oh, or even #nerd trivia. What's that? What's mass times velocity? What? Momentum. You could actually even get the momentum of a particle for what it's worth. Okay. Kind of cool. Let's apply some of this. Example 2. An electron, I'd probably underline the word electron, make sure I use the right information. Moving that fast enters a perpendicular, okay, they are at right angles, 0.545 Tesla magnetic field and traces out a circular path. What's the radius of the path? We're moving in a circle. What's pushing me in a circle? Why, magnetic force is pushing me in a circle. What's the magnetic force on a charge? Why, that is QVB. What's the what's the centripetal force? Mass times, which acceleration, Mr. Dueck? V squared over R. And Riley, I can go like that. Riley, what's this question wanting me to find? Can I show you the most common dumb mistake that kids make? Don't write this down, but I guarantee I'm going to, by the way, I like this question, I like this question, I like this question. You can guarantee it. But every year, Ben, I see this. What did you say we're trying to get by itself? R. I see kids go, QB over MV equals R. Call me silly. I think what they still have is that. Don't do that. I got nothing. Cross multiply. Don't do that. Write this down. You know what I would do? I would move the R up to there, and I would move the QB down to there. I think you're going to get this. R equals, I think the MV stays, and the QB goes down there. Mass. It's an electron. We've done this dance before. V, speed, not voltage, because no wings. 3.2 times 10 to the 6th. Yes? Over Q. It's an electron. And you guys are cluing in when I say that. I'm saying, it's on your sheet. Make sure you use the right value. 1.6 times 10 to the negative 19. Yes? B. Oh, magnetic field measured in 0.545. Now, here's the problem with this question. I made up these numbers, and they're terrible numbers. You're going to get a really, really small radius, which is stupid. And in fact, last class, I made a little note on my computer. In July, on my screen, a reminder will pop up reminding me to change these numbers because they're terrible. I think you get something in the 10 to the negative 5 range, which is crazy small, because 10 to the negative 3 is millimeters, so 10 to the negative 5 would be hundredths of a millimeter. I'm not even sure our human eyes could spot that. But anyways, Mr. Dueck making up bad numbers. You get, what do you get? That's way too small a radius. What I need to do is make it travel faster. And you know what? I made way too big a magnetic field. 0.54. Remember that 4 Tesla MRI machine was huge. This is 1/10 as strong as that, which is still pretty big. Anyways. You know what? A better question, a much more realistic diagram is example 3. I stole this from an old provincial. First of all, is the diagram right? Look at your picture at the beginning. Which way is this proton traveling? Point your thumbs up the page. Which way is the magnetic field? What do those X's mean? Will it get oh yeah, it will get deflected in a circle as it keeps moving a lovely circle. Right? Because that's the direction of the force. Darian, what's number 6? Example 3, but it's a question 6, asking me to find. Speed. What path are we tracing out? What's pushing us in a circle? Which force, oh pray tell? Why, Darian, magnetic force is what's pushing us in a circle. This is my starting point for this. I derive the rest each time. Darian wants me to go QVB because I did hear him say V final. I think it's just V because there is no initial and final, but I know what you mean. And it's going to be MV squared over R. Darian, I can cancel out one of these. Darian, how would I get the V by itself?
Times by R divided by R.
Yep. Q B R over M. Q. It's a proton. (1.6 times 10 to the negative 19). B. Teslas. Instead of writing 2 times 10 to the negative 2, can I just go 0.02 because that's less writing and that's the same thing? R, 3.25. M, it's a proton. I know it's 1.67, but I can never remember the 10 to. 0.02 times 3.25 divided by 1.67. Scientific notation. That's the wrong button. Scientific notation. You should get a speed in this 10 to the 6. Yeah, okay, that looks about right. They move fast. 6.23 times 10 to the 1, 2, 3, 4, 5, 6. Yeah. Okay. Turn the page. All right, that's for a single charge. What if you keep the charges, Noah, inside a wire? Because really all a current carrying wire is a bunch of charges marching in step together. How big's the force then? And you can actually come up with the equation from the one we just used. Jeff, you can actually write F equals QVB. You can rewrite that, you can drop the Q down, leave a space, drop the B down, but you can write V, as long as you're not accelerating, as distance over time, meters per second. So, well, what that means then is, as an equation, the magnetic force on a wire depends on, Cole, what's that right there? Okay, there's going to be a capital B in the equation. Depends on the magnetic field strength, which makes sense. Stronger magnetic field's going to, remember, by the way, remember the jumping wire video that I showed you? There was definitely a force on that wire. It was enough to make it jump, or when they flip the current, collapse the entire apparatus. So it's a pretty big force. What else does it depend on? Circle this. What's Q over T? We just did it in this previous unit. I heard it. Also depends on how much current you send through the wire. And, okay, so I used the B, I used the current. Then there's some kind of a distance. It depends on a distance. Which distance? Turns out it depends on the length of the wire. So we use a lowercase l for length. And I always write my lowercase l's as a handwritten L. Why would I not want to write an L like that? What's that going to look like to all of you? The number? So get in the habit, if it's a lowercase l, do it in cursive. In fact, I even think on your formula sheet it kind of does that, does it not? Yeah, okay. F equals Bill. Oh, wait. Except. The magnetic field and the current have to be perpendicular, otherwise your right-hand rule won't work and there is no force. Basically, all we're saying is, oh, instead of one charge, how many charges have you fit in that length of wire? That's the force. Example 4. Find the magnetic force and the direction on the wire. On the what? So it's a magnetic force, but I'm not going to use QVB. I'm going to use Mr. Bill. And I think everything is in the diagram, Jeff. If you look at the units, how big is the magnetic field in the diagram?
6 Tesla.
Tesla, 6. That's by the way, that's even bigger than that MRI machine. That's huge. Jeff?
Yeah.
See the direction of the magnetic field? See the direction of the current? Are they perpendicular? Are they at right angles to each other? So this will work. Okay, I should have done that check first. Keep going. What's the current?
5 amps.
And then how long is the wire that's in the magnetic field? Don't say 70. Please do the unit conversion.
0.7.
Thank you. Now, Jeff, here's where you can impress me. Can you do it in your head? 6 times 5 is
35.
30. 30 times 0.7, it's going to be the same as 3 times 7. 21 what? Force units. Now, direction. What direction is the current? Point your right thumbs, and this time I'm keeping my hands tucked so you can't copy me. Point your right thumbs in the direction of the current. Look at the picture. Extend your fingers in the direction of the magnetic field. So for me, I have to go like this. Yeah, you know what? Is it into the page, I think? Yes? My palm is pointing into the page. I think if it's face down it's on your paper, it's a little easier for you guys. Right? Or you could go like that and just use the symbol, and I'd figure it out as well, because that's the symbol for into the page. I usually write it out in English because I'm worried I might do the wrong symbol in a brain cramp. Now we can start to reverse engineer this. You may recall, Jake, last lesson, Jacob, I said, as soon as I showed you that jumping wire, I said, we've just entered the realm of how we move things electronically in machines. So example 9, suppose I know how big a force that I need to move whatever part we're talking about. How strong a magnetic field do I need? Because example 5 here is asking us to find a magnetic field. Is there a wire? In example 5, this next one? Yep. And I quickly double checked. Oh, Darian, there's the magic word. They are perpendicular, so there is going to be a force. So I can start out by saying, hey, magnetic force is going to be Bill. But Ben, what's this question wanting me to find?
You want to find the magnetic field.
Magnetic field strength, which is which variable? Yeah, it's B. Every time I ask this, I like this question, like this question, like this question. Kids give me F. They think that's the magnetic field. No, that's a force. I want B. Magnetic field is measured. Oh, what's it measured in? Teslas. Okay. Let's get the B by itself, Ben. How? Yep. So it's going to be the force. You know what? I'm going to write it as 0.001 because that's what 1 times 10 to negative 3 newtons is. And it's going to be divided by 12 and 5 centimeters. Ben, how many meters? Yep. Okay. How big a magnetic field will you need to exert a 0.001 Newton force? (1.67 times 10 to the negative 3 Teslas? What if, Jeff, in your machinery, you need a force twice as big? Oh. You can either, if you need a force twice as big, double the magnetic field, or you could double the current. But now we're starting already, in terms of designing machinery and moving parts, Darian, to say we can customize things. But the real question then, how the heck can you customize this magnetic field, Mr. Dueck? You just said make it twice as big. How do I do that? Next page. First, I got to show you a cool application. How many of you have seen the movie, and it's 20 years old now, called The Hunt for Red October? Any of you? So it's a classic. This will make more sense to you guys. The premise in the movie is that a submarine has been invented by Russia that is super quiet. It has a magneto-hydrodynamic caterpillar drive. What they're saying is it has a underwater jet engine with no moving parts. Here's the physics behind it. Okay? And as I understand it, military, they are trying to use it or apply this, and they may have it already. What I didn't draw in this picture, here's a side view of a submarine. What I didn't draw, and don't write this down, is closest to us, I have a big metal plate right there. Don't write that down. And I'm going to charge the plate positively. See, the problem is if I put that picture in, you can't see the guts. But imagine that closest to us, the north and south magnet, they're connected by a piece of metal, and I've charged that with a positive charge. Seawater is conductive, and so because I've charged the plate closest to us as positive, the electricity is going to go through the water to the metal sub. That's what that is right there. It's heading away from us. With me so far? And I got a north magnet at north pole and a south pole. Hey, which way do magnetic fields point from what to what always? Hey, let's draw in the magnetic field lines. There's a magnetic field lines going like that. Is the current and the magnetic field perpendicular? Yep. Point your right thumbs in the direction of the current. You know what? Let's all do it up here. Which way is the magnetic field? Which way will there be a force exerted? Out the back. What will the force be exerted on? What did I say was carrying the current? Seawater. You're going to have seawater squirted out the back like a jet engine. Do you see any moving parts? What you've just invented is a really quiet sub. Because you know what noise it makes? Instead of the noise of a turning propeller, the sub in the ocean makes the noise of water moving. Try finding that in the ocean. So there's the physics of that. Cool application. But going back here, I said, Darian, it'd be nice if we can customize our magnetic fields. And it turns out it's ridiculously easy to customize how strong you want your magnetic field. How? With a solenoid. With a solenoid. Ampere did a lot of research with solenoids, and he found three things. He found the more times I wrapped the wire around, the more turns of wire, the stronger the solenoid. So he said, I think in the equation, the number of turns, you know what, I'll use an N. The number of turns of wire, N, he says, it's going to be on top, because more turns means bigger. He said, I also found that I could generate a bigger magnetic field by beefing up the current. I know I is going to be on top as well. So he found to make a solenoid stronger, wrap more wire around. You want it twice as strong, wrap twice as much wire. You want it 5 times as strong, wrap 5 times as much wire. You want it 17 times as strong, and is that customizable? Wrap 17 times as much wire around. Or you can make the current 17 times as strong. But he found there was a third thing it depended on, how long the solenoid was, but this was the opposite. The longer, the weaker. So he said the length must be on the bottom in my equation, because when L gets bigger, magnetic field gets weaker. He found this. The magnetic field strength from a solenoid depends on these three things. The number of times you wrap the wire around. The current. But it's reciprocally dependent on how long the solenoid is, because longer was worse, not better. But to make it an equation, we need to put a constant right there. Just like for gravitational field, we had to put a big G, 6.67 times 10 to the negative 11 right there. Just like for electric field, we had to put little k, 9 times 10 to the 9. We're going to have to put a constant there, and this is your final constant of the year, but it's one of the most impressive. Turn the page. Ampere found this. The magnetic field created by a solenoid, and I'll put a vector because we can't get the direction from the right-hand solenoid rule. North was, hold it in your hand, thumb points north. Mu naught, mu with a 0, and you can say mu 0, Noah, and I'll figure out what you mean, but my high school physics teacher was British, and so in his honor, as an homage, because I learned to call it mu naught, I will always call it mu naught. Times N times I over L, where N is the number of turns or wraps of wire, I is the current, and again I'm using a lowercase cursive L, so you don't think it's a 1. L is the length of the solenoid. And mu naught is on your sheet. What is mu naught? It's right where K is. It's right where big G is. It's going to be in that same section somewhere. 4 pi? Pi? Really? What does pi have to do with magnetic field? Pi shows up in some weird places. 4 pi times 10 to the negative 7. This constant has one of the best names ever. It's called the permeability of free space. Kai, what did you learn in school today? Mummy, I learned about the permeability of free space. Oh, Kai, you are ever so clever. Come on, that's a great name. By the way, best name for a band ever in my mind. Oh, come on. Either the mu naughts or the permeability of free spacers, whatever. Okay. Nerd note: pi rears its ugly head again. Now, here's the problem. So mu naught, 4 pi times 10 to the negative 7. When we do these next few examples, every one of you needs to try your calculator, because some of your calculators won't be able to type that. And I will show you a workaround. So, there's a second version of this equation. Okay? Sometimes, in fact, this is the most common one in industry. If you go buy a solenoid in an electronics store, you won't tell them how many turns and how long it is. Instead, you'll tell them the rating of your solenoid in turns per meter. They'll just have already reduced that as a fraction for you. So the second version of this is mu naught little n times I, where little n is turns per meter, and it's actually already n divided by L. They've done the math for you. How will you know to use that? Because when you read the question carefully, you'll see turns per meter. These are both on your formula sheet. That's why it says B equals, and then right next to it equals again. Okay. And I think now I've done the top 4 equations of the electromagnetism. Okay. And those are all the ones we'll be using in this unit. The second half is the next unit. Let's try some of this. But this is how you can customize a magnetic field for whatever your industry needs. Example 7, a solenoid is carrying a current of 4.2 amps. The solenoid is 1.2 centimeters long. It's made up of 750 turns of wire. How strong a magnetic field will it create at its center? There's a solenoid. It's asking, what's it asking me to find? B. It's asking me to find. By the way, what's example 8 asking me to find? The next one. Find the, you know what? The difference is in number 8, I'm using the coils per meter. We'll talk about that. Let's go to example 7. Example 7, it's going to be mu naught times capital N times I over L. Did they tell me capital N, the total number of wraps or coils or turns of wire? Yeah. Did they tell me the current? Yep. Did they tell me how long the solenoid is? Then we're good to go. So it's going to be 4 pi times 10 to the negative 7. N is 750. I is 4.2. All over, careful, 0.012, because it's centimeters. All of you need to try typing this, and many of you are going to get an error. If you have a TI calculator, you'll be okay. If you have a Casio, I know you'll get an error. If you have a Sharp, I'm not sure. Who got the error?
I'm going to get one. So.
Okay. So the error is this. Your calculator can't handle a pi symbol next to scientific notation. So for you guys, you'll have to type, instead of 4 times pi, pi times 4 scientific notation button, negative 7. You're going to have to flip these two around.
Wow. If we have a constant for mu naught, we just use that?
If you have that built in, I'm impressed. Yeah, sure. See if you get this. Double check to make sure it's the same one we're talking about. You're getting the same answers in this lesson, but then yeah. Shouldn't. Don't clear stuff. Gotta be careful. You have to go pi times 4. You can't go pi 4.
Okay. Yeah, I made the same mistake.
Okay. It's a software issue. Whoever wrote the software didn't anticipate treating pi like a number. I suspect it treats it like an operation. What do you get? And I'm deliberately not doing this one because this is my way of forcing you to find out whether your calculator works or not. What do you get? 0.33? 0.33 what? No, 0.33 what? Units.
Oh,
Teslas. So, let's suppose, Carl, that you're in a factory and instead of 0.33 Teslas, you need 0.66 Teslas. You buy a solenoid that either has 1,500 turns of wire, or if you're stuck with the solenoid you bought, you change the circuit. How many amps? 8.4, double that. Like, it's very customizable. Or you could make it twice as small, but 1.2 centimeters is already pretty small. That would be a little tricky to do. But you can now start to order magnetic fields on demand. Josh, on demand. Works great. Trevor. I thought it twice and I canceled it and I corrected myself in my brain and I got it wrong on the correction. Good gosh. Example 8. Example 8 wants you to find the field and the direction. Now let's do the direction first. In this picture, what you're doing is you're looking right down the center of the solenoid, but I just didn't draw it three-dimensional. In other words, in this picture, if I'd drawn it 3D, it would have looked like I just didn't draw all that in. Okay? So let's do the direction. That means we're going to hold the solenoid in our hand. We can either hold it this way or this way. Oh, we curl our fingers in the direction of the current. I have to hold mine this way, yes? My thumb points north. Which way is north? Out of the page. So, you know what? If you did it with symbols, right? Or you could write it. That's going to create a magnetic field coming towards us. How big? Now, if you don't write this down, if you started out going very quickly, you'd notice no L. They didn't tell me the total length. Now, or you could cleverly say per meter, maybe L is 1, which is really kind of what we're saying. What we're saying is here, I gave you the number of turns per meter. We have to use the second one, n, little n, times I. It's going to be 4 pi times 10 to the negative 7. 2,550 turns per meter times 10 amps. How big a magnetic field will this create? Does yours have mu not programmed in? Oh, cool. Do you get 0.032? Yeah? Teslas. What if you wanted a magnetic field twice as strong? Either run 20 amps through it, or you have to buy a new solenoid, and your new solenoid would have to be 5,100 turns per meter, if I doubled that correctly. I think I did. Because mu naught's a constant. We can't change that. The permeability of free space. So I've said you can order customizable magnetic fields. Example 9. Suppose you're building a machine and you've got room for a 30 centimeter solenoid. And you know that you need a magnetic field of 6.28 times 10 to the negative 3 Teslas. Call up the factory. How many turns of wire should they wrap around this solenoid if you also know that you're going to be putting 5 amps through it? What's this question asking me to find?
Turns of water.
Which is which variable? N. So first of all, let's write down magnetic field from a solenoid is mu naught N times I over L. But Kai, you're right. They want me to find the number of turns of water. N. How would I get the N by itself? What will I do with the mu naught and the I? Divide them. What will I do with the L? Times it. So I'll get this. N is going to be B times L divided by mu naught times I. You know what? As far as I'm concerned, Jeff, there's 1, 2, 3, 4 variables. Any 3, I can ask you to find the 4th on the test. Is fair game as far as I'm concerned. Is that okay, Riley? Let's crunch the numbers here. The number of turns, and I think this is going to work out nearly evenly. I tried to make it do so. It's going to be 6.28 times 10 to the negative 3 Teslas. The length is, careful, don't write 30, 0.3. 4 pi times 10 to the negative 7. Current 5 amps. What'd you get? 300, like 299.9 something. Yeah, yeah. I think I started out with 300 and worked my way backwards because I kind of figured I didn't want to have half a turn of wire. That didn't really make sense. So 300 units. I guess turns of wire. Okay. Yep. Have I explained the homework yet? Am I going to let you go before I explain the homework? Will I ever let you go before I explain the homework? Nope. Because that brings us to the end of the lesson. What's your homework? Jeff, I like number 1. And number 2. And number 3. You know what? It's everything skip 8. Nope. Can you look at question number 2, please? Once you've done everything skip 8. Question number 2, look at the picture. What force is pulling down? Gravity. What force is lifting up? They did FM for F magnetic force, not field force. Oh, and they're balanced. You know what? Here I can say that. I can say mg equals, is the magnetic force through a wire or through an individual charge? Bill. And now I can solve for whatever. I'll let you think about what direction the magnetic field has to be for this to work, but I'll talk about that next class. Okay? I got a cool video to show you.